nice introduction. I am delighted to be here. Actually, this is my fifth trip to Spain. So Spain is one of my favorite countries. I keep coming back to Spain. And it's a great country with great people. So I'm delighted to be back to Spain. And I see some familiar faces, old friends, Richard, Professor Corona, good to see you, and some others. Okay, so now we are in business. So this time I decided this topic. I proposed a couple of topics and conference organizers chose this topic, recent advances in machine learning and classification algorithms. So let's go, I have to go here now. Not this one, page up. Page up. No. So this is the one? Yeah. All right. Very good. So we want to talk about machine learning. Machine learning is becoming prevalent in every part of the society. More and more we're going to see it. You see it in driverless cars, and you see it all over the place. It's a key technology in the 21st century. So, types of machine learning algorithm, we can divide them into two categories: supervised learning, going back to backpropagation, that proposed in 1986. Then later on, probabilistic neural network, and we developed the so-called enhanced probabilistic neural network. And more recently, we developed a brand new algorithm called neural dynamics classification. So I'm going to talk about those today. And then the second category is the unsupervised learning. And here we extract common or hidden features encoded in available data points. And examples of the restricted Boltzmann machine and deep Boltzmann machine, which has attracted a lot of attention, and also deep convolutional neural networks. So, different types of supervised machine learning algorithm can be divided into two categories: classification. Output is in the form of categories, there are different categories. And the second type is regression. Outputs are in the form of real values, and examples are BPNN and recurrent neural networks. So let's look at a simple example of classification. And let's say class 1, you see those apples. In class 2, apples. In class 1, the color is green. In class 2, we have oranges. Now we have testing data on the left. And how do we classify this? So as human beings, that classification is very easy, simple classification. If you want to develop a machine learning algorithm, that becomes a big mathematical problem. It's not that simple. And the second simple example is on the right. So depending on the color or the shape, you can have different results. Okay, so example of supervised learning, regression, a type of learning. Here, imagine we want to estimate the strength of concrete. Concrete on the left you see consists of different materials. So these are different materials: cement, slag, fly ash, etc. On that basis, we want to estimate compressive strength, and that is an example of a regression supervised learning. And probabilistic neural network, and the key idea here is probability of a data point being similar to its classmate is increased when classmates are closer to each other and further from non-classmates in the Euclidean distance. And usually a Gaussian probability density function is used in this probabilistic neural network. And you can see that on the right here. So here you see different layers of probabilistic neural network. And we develop enhanced probabilistic neural network. And in order to improve the classification accuracy, so instead of having a fixed Gaussian spread, we modify the Gaussian spread based on the local properties of the samples. So instead of defining a fixed sigma for training in the equation here, we define sigma n as that sigma times an alpha n. Alpha n defines the number of training data points with the same class as yn in the local hypersphere. We define a hypersphere, and that can increase the accuracy of the classification substantially. So, as an example, we developed this computer-aided model for diagnosis of Parkinson's disease. So this paper was published recently. So how do we make diagnosis of this disease? And this disease is very prevalent, and Parkinsonism consists of different manifestations here. So diagnosis of Parkinsonism is not that simple. You can see that here examples how it is done, and there are various things that neurologists consider here. And today, actually, I have a neurologist with me here. My wife has given me the honor of joining me. She rarely comes to conferences with me, and she's here. And and she corrects my neurology. And if you remember, 2 years ago, my entire lecture was about EEG-based diagnosis of neurological and psychiatric disorder. That was the entire lecture. But today, this is my only example of neurology. So my research covers many different areas. And so I also do research in neurology. So anyway, so you can see that the complexity of this problem. And so here you see, you have to look at all this to make the diagnosis. So we develop a model using that enhanced probabilistic neural network for the diagnosis of Parkinson's disease versus SWEDS. That's scans without evidence of dopaminergic deficit. That's another kind of disorder. So we develop a model to distinguish between the two. Distinguishing the two is not such a simple matter, even for a trained neurologist. And for data, we used this Parkinson Progression Markers Initiative. It's a multi-center database, and we have 189 Parkinson's disease and 62 SWEDS, plus 450 healthy controls. So you can see that the input data, the number of input data is very large. So that explains the complexity. The number of input items is very large. So here you see some results of using our machine learning enhanced probabilistic neural network algorithm. And of course, we use other popular methods. So, classification theory and support vector machine, another very popular machine learning algorithm, KNN, K-nearest neighbors, and probabilistic neural network. And you can see that enhanced probabilistic neural network gives you the highest accuracy. So, to summarize this, machine learning algorithm can aid neurologists in evaluating multiple sources of data for diagnosis, and EPNN, enhanced public neural network, displayed greatest accuracy and robustness to missing data. Also missing data. Data is not complete for every patient. That's a major issue. Data is not complete for every patient. And then there are some medical conclusions here, and some medical conclusions that we learned. We didn't know and we learned. So then let's talk about unsupervised machine learning. First, the restricted Boltzmann machine learning. This is a two-layer interconnected unsupervised network, and this is inspired by the concept of energy equilibrium in physics. So there is a transfer of energy until there is equilibrium. On that basis, you have the solution. So here, in this approach, basically, we minimize the energy of network configuration defined analogous to that of a Hopfield network. So, summary, in every iteration of learning, the 4 phases: go up, compute the edge here, go down, and calculate, reconstruct X, remember the inputs, go up again, reconstruct H, remember the uncommon features, and finally update connection weights. So these phases 1 to 3 are performed using a sigmoid function, and this is repeated until you have convergence. So an example here is given using the face recognition. So, and the database is from the Yale University, corresponding to 15 individuals. So, and the learning is actually represented in these weights. So you can see that this is a testing example, and this is what we learned. So these faces are close to this, then the learning is successful. However, this restricted Boltzmann machine has disadvantages, requires a large number of iterations to learn properly, has only 2 layers, limiting its memory capability, not effective for large problems, And more we are dealing with larger databases. And there is also high chance of overfitting due to a small memory size, because there's only 2 layers. And also inaccurate reconstruction of inputs in large problems due to the small memory size. So to overcome these shortcomings, deep Boltzmann machine was proposed, and here we have several layers of RBMs. Each layer of hidden layer of each RBM is the input layer of the next RBM. Here you can see that. So this simulates several layers of neurons in human brain to extract features. So here we have 2 parts. There is this encoder and there is the decoder. Encoder and decoder. Encoder, brain ability to extract features, and decoder, brain ability to remember. So encoder is a flipped version of the decoder. And here, a pre-training process is used to boost the learning speed. Hidden features can be used as input to a supervised machine learning algorithm to use this as a supervised machine learning algorithm. So here, each layer of RBM is pre-trained for a few iterations simultaneously, then the weights and biases of each layer of DBM are fine-tuned with a few more iterations using the backpropagation techniques. So the advantages here are a few number of iterations to learn properly. So this deep Boltzmann machine has attracted a lot of attention in the past few years. Why is that? Because it is used in the smartphones, Siri, for example, on iPhones, it is used in digital cameras, detecting faces, driverless cars, etc. So this has attracted a lot of attention. And because advantages, few number of iterations to learn properly, large memory capability to solve large problems because there are many layers, reduced chance of overfitting due to high memory, extracting features from the features extracted in the previous layers consecutively that provide a powerful perception and recognition capability and more accurate reconstruction of inputs. So this is one of the most popular. So to summarize here, this deep learning approach is accurate in large data problems. For a smaller problem, that RBM is ample enough for proper training. And the most recent deep learning tool is the deep convolutional neural network, similar to BM, but with much higher memory capability. So we use this to solve a complex problem. And this complex problem is estimating sale prices of real estate units. So real estate is often associated with global economic crisis. This is a huge problem. When the bubble bursts, the economy goes down. That is true in every country. And can we estimate the future prices of real estate? This is a very complicated problem. If we are able to estimate, we can prevent the bubble. So this is a very important problem we are addressing. To be able to estimate the future price of the, so if we can estimate, then the builders will not build. There will not be overbuilding. So we can avoid this bursting of the bubble. So the problem here is a large number of variables affect real estate price dynamics. So, but if we can estimate it, then we can deal with the build or not to build gauge, and gauge the sale market. So if you don't overbuild it, then you won't have the bubble here to burst. So the model here takes into account any number of variables affecting the real estate price movement. And as I mentioned here, can assist construction companies to address the build or not to build question and avoid oversupply and subsequent crash. I want to say something. I'm giving you many different examples. For each example, I could spend 1 hour to go into detail. That's not the intention. This is the keynote lecture, so I'm covering many different problems here. But I want to give you I want you to understand the significance and complexity of this problem. That's why I'm showing this. The number of factors involved in this problem to estimate the future real estate price. So here you see economic variables and indices for residential. This is only for residential condos. Look at the list. Look at the list here. And then we have physical and financial properties. So we have a large number of variables. Very complicated problem. One of those problems that you can argue cannot be solved. Just like driverless car, some people say driverless car doesn't work, it's too complicated. So we developed this machine learning model for estimation of the sale price of real estate units. And here you see how the variables are modeled. And so we have to do data reduction. The question is, out of so many different factors, which one affect the most in order to reduce the data and make this network learning process more manageable. And this is part of that. And for that, we use a non-mating genetic algorithm to generate new population in each iteration instead of crossover and mutation to increase the chance of finding a near minimum solution. And we applied this to some data we had, and data was obtained from this city. Do you recognize this city? What is this city? Anyway, I'm sorry? What is this city? This is Tehran. And data was collected. The person who worked with me was from that country, and he had data. And we use the data from that country, and Tehran is a huge city with lots of high-rise buildings, lots of data. So here are the results. The results here is, we can see that the deep neural network, we can solve the problem at a fraction of the time. So you see, BPN can also solve the same problem, but it requires much more time. That's the bottom line. So DBM is effective for learning of the high-dimensional and complicated pattern recognition problem. And this model that we develop is not limited to the real estate problem. It can be used for construction cost estimation, transportation cost estimation, fabrication cost estimation, and sale prices of different construction materials. So here I want to give you another example. So we develop here a supervised DBM for estimation of concrete properties. So problem, how do you determine concrete properties? Each time we have to do a test, and test is costly and time consuming because you have to use destructive methods, labor intensive, trial and error requirement. So the model here takes into account any number of variables affecting the concrete properties, is able to reduce the trial and error experimental process. So here is the supervised DBM for estimation of concrete properties. And the input values are here: cement, fly ash, coarse aggregate, what percentage, what ratio of different materials should be used in order to achieve certain concrete properties. So we tested the data using machine learning data from the University of California, UCI repository. So inputs are here, and output is a 28-day concrete strength, and result is accuracy of 96.5%, and compared with 91.8% for BPN. And the model is not limited to concrete, can be used for other materials like asphalt and pavement. Okay, now we are getting to the good part. So I'm going to talk today, from here now, I'm going to talk about a new classification algorithm that we developed. And before that, I have to talk about this optimization model, neural dynamic optimization model of Adeli and Park. This was patented. It's very rare to patent an algorithm. It was patented. And most of you probably have not heard. This is a very powerful optimization algorithm. And that's the reason we applied for a patent. I've written many papers. I only have one patent because it costs money to apply. It costs about $20,000 in the US. Not a whole patent. I have one patent. And most of you have never heard of this. Do you know why? Because you can't use it. It's patented. The patent will be done next year, 2008. You have a 20-year life cycle. But this is a very powerful optimization algorithm, and we use this to develop a machine learning algorithm that comes next. So we model our optimization algorithm as a dynamic system where the optimum solution is the equilibrium point. So that's the way we look at it. And we use 4 different mathematical concepts. Neural dynamic concept that directs the evolution of the solution. Lyapunov stability theorem ensures continuously decreasing convergence. Penalty function method reduces the violation of constraint. And finally, Kuhn-Tucker condition guarantees optimality. And let's go here. So the optimization problem is formulated, modeled as a dynamic system with an equilibrium function where the optimum solution is the equilibrium point. And then Lyapunov stability theorem guarantees that for any starting point, the solution for dynamic system would always approach the equilibrium point without increasing the objective function. So, and here is some more equation here. So, we used this actually 20 years ago to optimize super high-rise building, to 144-story structures. So this was done 20 years ago. This was the tallest building ever designed at that time. And so so we had to do it on a supercomputer. This is a very large scale problem. We have like 600 optimization variables, more than 20,000 members, and like 40,000 constraints. Very large scale problem. And solving such a large scale problem can create convergence and a stability issue. And what you see here is the beauty of the algorithm here. You see, this is a convergence. Each time it goes down. And that's the reason we applied for a patent. So the model provides a smooth and very stable convergence curve. So this is another example of machine learning. And so we use that non-dynamic optimization algorithm. And here we have a model for concrete mix design. How do you design concrete? Concrete consists of different materials, fine aggregate, cement, admixtures, coarse aggregate, water. What should be the ratio in order to reach certain strength? So this may be a low-tech problem. So we are integrating low-tech with high-tech. And the result is saving millions of dollars for the construction industry if we do that. So what's the problem? Currently, there is this American Concrete Institute. They have a standard. They provide rough guidelines how to mix them in order to have certain strength. And this is, then based on that, then you got to make the test. You have to go to the lab and test and get the strength. So it is cost and time consuming lab work, and cost of ingredient is not directly addressed in the ACI code. There is no minimum cost involved here. And we developed this model for concrete mix design that can take into account any variation in the properties. And this approach, mixed design, provides a cheaper solution than the one in the code. So we here define this as an optimization problem with cost as objective function. We minimize the cost, and then we have 4 sets of constraints, and we solve it. We can solve this actually using any optimization algorithm, but we use the optimization algorithm that I mentioned a few minutes ago. So the desired constraints, for the desired constraint means what strength you want, what properties you want, and for that we use a classification algorithm, and that acts as a virtual lab to estimate the desired properties of concrete. So we introduce the concept of virtual lab. Rather than going to the lab and making the test, we use a classification algorithm which is based on prior data. So a model for concrete mix design using NDAP, non-dynamic optimization model of Adeli and Park, and the virtual lab concept. So we have objective function to minimize the cost, and then we have inequality constraints, ingredient constraint, technical constraint, and a set of desired constraint. So the problem is quite mathematically, has to be formulated mathematically. And here you see the nature of the constraints that we have. On the right, technical constraint defined by code development agencies. For example, ranges of water to cement ratio. And desired constraints are address the desired ranges of construction and structural properties that you want. And here we use the machine learning concept to develop a virtual lab. Class 1 means the desired, you are achieving the desired properties. Class 2 means not achieving those desired properties. So the desired constraint based on previously collected mixed design that are combined into one constraint. And then here we can use PNN or enhanced probabilistic neural network. And then we verify this using two examples, one from the code, ACI code, and one a modification of that to make it more examples. So the loss of numbers here. So I just want to tell you, look here, this is what you see, this is the cost. And the cost here is, and we use different machine learning method, SVM, support vector machine, PNN, and you can see that the best results are from enhanced probabilistic neural network, and you get the best result from that model. And so, to give you a sense of importance of this problem, and first, the best results were obtained by a combination of EPNN and non-dynamic optimization model of Adeli and Park. And here, our mixed design costs about 24% less than the solution provided in the code. This is a low-tech solution, and this is a high-tech solution. And as an example, the amount of concrete used in this structure, there would be $3 million cost saving. And the beauty of NDAP, look here, the beauty of NDAP here is this convergence curve. So here we use genetic algorithm, and PNN. Here is genetic algorithm, EPNN. You come here, and we use NDAP and PNN, NDAP and EPNN, NDAP and SVN, and look at the smoothness of the curve. The smoothness of the curve, that is the beauty of this neural dynamic optimization algorithm of Adeli and Park. So this is the summary here, and you can keep that in mind, the saving achieved here. So here is the summary. So there are other applications. All right. So here comes the best part. The best part. I kept the best part for the last. A new, but this builds upon the previous research. A new neural dynamic classification algorithm. This is brand new. If you're looking for a brand new classification machine learning algorithm, we got it. And this has not been published yet. Will be published later this year in IEEE Neural Network Journal. So what is the key idea? A transformation function is defined to generate a new J-dimensional feature space. We change our feature space, we change it to another one. That's the key idea. Transformation function is defined to generate a new J-dimensional feature space. And probability of the goal is probability of the transform form of X, that's the original feature space, being correctly classified should be higher in the transform space. We want the probability of correct classification to be higher in the new transform space. So original one and transform one. So the feature space is transformed such that the probability of a more accurate classification is increased. This is the key idea, and after that there is a lot of math involved there. So also this is shown here graphically. Look here, this original feature space, and we transform it. In a transform, we want these to be clusters together. Those in the same class to be closer to each other, and not in the same class to be farther away from each other. As I mentioned, this will be published later this year. So here we define a transformation function here. And this is our j-dimensional row vector of biases and j-dimensional column vector of ones for consistency here. So we use this probability density function, and in the previous slide, we have to define for you this one. So Z is the resultant of M transfer form of X. X is the original feature space. So we place all these Z in Z total called feature vector representative form of original features. So this is important. The Z total is feature vector representative form of the original features, FVR. So here you can see, so the transformation function generate well marginalized feature spaces, and these feature spaces should lead to a well marginalized feature space where this belongs to the new set. And how to find these called transformation parameters. How do you find these parameters in order to bring those who are in the same class together and those who are not in the same class further apart from each other? So to determine this, we use that neural dynamic optimization model of Adeli and Park. So here it is defined: a minimization problem, an objective function plus two sets of constraints. And objective function reduce the total Euclidean distance between classmates and constraint marginalized non-classmates. So marginalized non-classmates, and that's the way we define it. And here is some math for this, the inequality constraints. So what do they mean? This one means the idea is to push training data points in class M into a hypersphere with radius Rm. And this one, the second one, pushes training data points in classes other than M out of the hypersphere. And the third one keeps the radius positive. We want the radius to be positive. And then this optimization problem is solved by adapt. So the dynamic system corresponding to class M is defined like that and solve iteratively. I think you have seen enough math. So let's go show you some results. And first, we started, just like anyone else, using some benchmark problem to test this. And so these are 6 standard benchmark problems. You find them in the UCI database, UCI machine learning database. And here you see number of data points, number of features, number of classes, the number of variables to be optimized, 126, 33, 54, 246. So this gives you some idea about the complexity of the problem. And this is an example of results showing regulating the new feature space in the wine problem, So you can see that how we can bring the clusters together. We can bring the clusters together here. And here is the iteration process. It's very smooth, very smooth. And here you see the result. And with other classification algorithms. So here we have used RTT is different testing to training ratio. P stands for probabilistic neural network. E stands for enhanced probabilistic neural network. S stands for support vector machine. And N stands the new neural dynamic classification algorithm. So you can see that here, in almost all cases, we get the most accurate results. Then we went to a more complicated hand recognition problem. This is a large problem. This is a large machine learning problem. This is also a test benchmark problem, but more complicated. So hand recognition problem, and this is known as MNIST database, and we have 28 by 28 pixels. There are 60 training examples. In our work, we use 10,000 of them. So 10,000 of them, 10,000 for testing. And look, we have 23,550 variables to be optimized. Very large scale optimization problem. And we have more than 100,000 constraints. And we perform here 300 iteration. And this had to be done on a supercomputer. So we did on a supercomputer at Ohio Supercomputer Center. And here is that you see some examples of accuracy results for RTT of 50%. PNN gives you 65%, EPNN gives you 65%, and AC gives you 88%. So you get the highest accuracy from this new neural dynamic classification algorithm. And here, I'm supposed to have a video. Somehow my video is not shown here. So what you can see here, I have a video, but I don't think I can. Oh, here, the video is here. But before I go to video, I may need your help, but let me explain this a minute. So here is sample examples of marginalizing, and blacks are classmates and green dots are non-classmates. So we want to separate them. So this is the first epoch, and this is after 300. Look here, they're all mixed. They're all mixed. And after 300, they are separated. Classmates versus non-classmates. And here's another one. Epoch 1, and after epoch 300. So see whether I can get this video going. Let's see, how do I? No, it didn't go. Can you go here and? Yes, inside the presentation. So if you tap there twice, it doesn't go? Okay, we're gonna skip it. We can skip it. No, it's on the web. So it's okay, it's okay. It's a video of how this is done from epoch 1 to 300, so you can see. It's like a movie. If you're interested, I can send you the link to the video. So, I don't know how much time I have. So if I'm out of time, I can stop right here. I'm sorry? 5 minutes? 5 minutes, okay. So I brought you, and I gave you an overview I started with an overview of machine learning algorithms, and you went to the latest that we developed that will be published soon. And then we tested that using benchmark problems. First, the 6 ones were easier, and the last one was complicated. So now I'm applying that NDC to another problem that cannot be solved easily. That problem is earthquake prediction. Can you predict earthquake? That's another problem. Some people can argue it cannot be solved. So we apply this to this earthquake prediction problem. So current systems are based on P waves. They give you a few seconds.